statements of the second law of thermodynamics. There are like several ways we can define this thermodynamics, second law of thermodynamics. But two most important statement of the second law of thermodynamics. One is actually called as the Kelvin statement, Kelvin-Planck statement, and one is called as the Clausius statement. In Kelvin-Planck statement, it's a like it is impossible to extract heat from the high temperature reservoir, directly convert into work done without rejecting into low temperature reservoir. Let's say like no process is possible whose sole result is the absorption of the heat from the reservoir and conversion of that heat into directly work done. You might have said like the 100% efficient heat engine is not possible. So it is not possible itself. Uh, we have studied like when we are saying like when we are in a thermal equilibrium, and when we are thermal equilibrium, that means like the entropy, the ds would be equal to 0. Change in entropy would be equal to 0. So when we are talking about the equilibrium process, there is no entropy changes, and when there is no entropy changes, actually there is no process going onward, and we are, let's say again I'm saying like we are in a equilibrium process. So that means like if we are talking about the single reservoir or high temperature single reservoir, so that high temperature single reservoir itself is in equilibrium. So in order to flow heat from the high temperature reservoir, you must provide with a sink. That means like you must provide with a low temperature reservoir. You must provide it with a non-equilibrium system. So when the system is now non-equilibrium, so in that case, the GS would be greater than 0, and that means like the system will move forward. So that the Kelvin-Planck statement is say like it is impossible to extract heat and directly convert to work done without rejecting into low temperature reservoir. So this low temperature reservoir is necessary in order to flow heat from the high temperature reservoir to a low temperature reservoir. So it is not possible to just have a reservoir and just leave it the reservoir, leave it as it is, and obviously convert directly into work done. So it is not possible. The Clausius statement say like no process is possible whose sole result is transfer of heat from the colder to a hotter body. As we say like the natural process, in natural process the entropy would remain constant or it will be greater than 0. That means like for a natural occurring process, entropy either it will remain same in equilibrium, or or it will actually increase from the initial condition. So in that case, if you are talking about the low temperature, going heat from the low temperature towards the high temperature actually, or getting heat from this temperature reservoir and throwing into a high temperature reservoir, that will not happen, because in that case it is definitely impossible to decrease the entropy. So in that case you are supposed to provide the work done when energy is losing, so that means like entropy would be increasing, and in that case you would be able to extract heat from the cold reservoir into the hot reservoir. So what we have got now, so we have got there exists for every system in equilibrium a property called as entropy, and we represent the entropy with letter S, which is a thermodynamic property of the system. For a reversible process, as we say, like equality will be only and only process, only possible when we have got the process which is reversible. And for the Clausius statement, ds was equal to dq by t. So make sure this equation is only and only valid for the reversible process. For the irreversible process, obviously this is not there. And obviously for the equilibrium, the entropy would be equal to zero. The limit, the total entropy change is constant, or the change in entropy is equal to zero, represent the breadth that can be done. So all these statements are equivalent, whatever you are saying, like whether we are talking about the equilibrium, whether we are talking about the reversible quasi-equilibrium process, the irreversible process, the non-equilibrium process. So whatever, in whatever condition, even the Kelvin-Planck statement, the Clausius statement. So whatever the statement we were saying, they are more or less same actually. But so looking at the first law equation and first law for the control mass equation, du was equal to dq minus dw. You can just see written over here. For the quasi-equilibrium process, or for the reversible process, now we call it as a reversible process. ds is equal to q by t, and dq is equal to now t ds now. For the quasi-equilibrium process, also dW was equal to PD. Putting them PdV and TdS in this equation, you will get the equation something like this over here. Checking the equation, you can imagine like pressure in here, or just looking at the notes over here. So you can just divide this in terms of bracket and square bracket. So pressure is an the intensive property, while volume is extensive property. Now you can imagine from this analogy, the temperature is intensive property. So that would mean like the entropy would be extensive property. And all these properties are now the state properties: temperature, entropy, pressure, volume, and obviously the internal energy. So you can imagine like the first law of thermodynamics. Now we can actually define it in terms of the state variables now. Now, as we define the first law in terms of entropy now, so you can imagine like we can use this equation for the to find out like which process will occur and which process will not occur. Let's say, for example, again, if I'm saying like if ds is equal to zero, that means like this equation, the first law will actually stay there, and if we are in an equilibrium process. And if let's say like the entropy is increasing, so that means like the process is happening, the first law process is happening. And if we say like ds is less than zero, so that means like that is impossible process, an unnatural process, or we have to supply energy to make the process happen. So now the first law of thermodynamics is actually now in terms of direction, and that means like whether it will happen or it will not happen. Summarizing the entropy is a function of state. We did define the state property now, and obviously for the state property, two independent intensive property would need it to define the total state of the system. Entropy is an extensive variable. That means like entropy per unit mass is there, and we can call it, and per unit mass we can call it as a specific property. The unit of entropy is joule per or kilojoule per Kelvin kg. For a system, that means like ds is equal to dq by t. That means like we are talking about the reversible process, the mathematic statement of the laws of thermodynamics. So I did say like what actually we are extracting from the thermodynamics laws. So the zeroth law, we define the zeroth law in order to define the thermal equilibrium. And defining that thermal equilibrium, we need to introduce a property, and that property was called as temperature. For the first law of thermodynamics, we did define the first law of thermodynamics because we need to find the law of conservation of mass and energy. And we did define the conservation of mass or conservation of energy with the help of the property, and that property was internal energy, enthalpy, and temperature as well. Now what actually second law say? So obviously there is no exact equation that what we can relate to the second law of thermodynamics. But first law of thermodynamics, there was a valid point, or there was a valid flaw in the first law of thermodynamics, and that was actually the natural flow of the process. So the second law was introduced, or second law is introduced to define whether which natural process will occur in a direction, one direction, or which natural process will not occur. So in order to define that second law, that natural process, that direction of the natural process, we need to define a property, and that property is called as entropy. And that for entropy, we define a rule, and that is entropy of the system, isolated system, never decreases. So we define with the two condition, whether it will be actually equilibrium, whether it will be actually a forwarding direction, or if we call it as a natural process, and we call, and another one we could call it as a non unnatural process. So that means like if entropy remain constant, ds is equal to 0, that means like we would be having a equilibrium process and the system will not move forward. And if ds is greater than 0, that means like it is a natural process and the system will move forward. And if we are saying like ds is less than 0, that is unnatural, and we cannot actually say like the system itself, isolated system itself, will go from high entropy towards the low entropy. So that means like it's a unnatural process. So that means like the second law of thermodynamics define the equilibrium, natural process, and unnatural process. So the concept of energy is not sufficient, and the new property must be appeared. This property can be developed, and the second law was introduced, in much the case that the first law and zeroth law was presented. Now let's have a final word on the second law of thermodynamics, and that include the entropy. So there exists in every thermodynamic system in equilibrium an extensive scalar property called as entropy, such that the infinitesimal reversible changes, that mean like quasi-equilibrium process, quasi-equilibrium reversible process, in which ds was equal to dq by T, where T is the absolute temperature and dq is the amount of heat received by the system. The entropy of the thermally insulated system cannot be decreased, and it is constant if and only if all the processes are reversible. With as with the zeroth law and the first law, the existence of new property entropy is asserted and its behavior is described in this lecture. I hope you understand this lecture. If you have got any question related to it, you can drop me a message in your classroom and I would be able to answer that one. Thank you very much.